I'll start with the thanks that Maike just ended with. So thank you, Holger Hanselka and Studica Olderock, for instance, for advising me, Holger Hanselka for getting me here in the first place, Bernhard Beckert for getting me here in the first place, but also Bernhard Beckert and Peter Schmidt for advising my undergraduate thesis and master's thesis, because this is the requirement before you do a PhD thesis. Hello, my PhD students from the US and so on. Doing a master's thesis usually is supposed to be a requirement before you do a PhD thesis, just so you know, FYI. And in particular, thanks to all my friends who come here, traveled so long and far, my students who came here from CMU and from LMU and all those places and so on. And also, I mean, Maike emphasized, I think, the research angle of how well the two of us, for instance, are welcome into the KIT environment. But there's also the personal level, right? I feel like the best possible research is the one you can do among friends. When you've got really brilliant people right next to you, you get along with very well, who then organize DFG, Sonderforschungsbereich, tiny little things and so on, just directly in the direction that your research is into and so on. That seems like a very warm welcome, so I very much appreciate that. But of course, I can't do anything without Laurence Böhnke either, who is running around outside managing everything, and I have a small attack on you. I really hope that she'll ultimately be in the room with us and we can all thank her then. I don't know when she will have time to come here, but I feel like it's not only the organizing, it's also even figuring out the right forms for organization that has kept her busy for a little while. I am privileged to be able to talk to you about my favorite topic, which is that of logic of autonomous dynamical systems. And that is, for instance, the dynamical systems analysis question to predict which control decisions are safe for aircraft collision avoidance, because if you're flying this plane, you should take care that there's other aircraft very close by and that everything inside this red shape here would be an unsafe control decision to follow, and the only good predictions are the ones that go that way and so on. This is, by example, the dynamical systems question, where dynamical systems describe the mathematics of change, and dynamical systems describe the future. Predictions for systems that already describe the future sounds like it's a triviality, but there's a big difference. The difference is that the dynamical system describes the future only implicitly. It tells you, well, at the moment I'm going that way, at the moment I'm flying this way. But the prediction question is something long-term. It's the question that says, if we sit on a plane that is described by this dynamical system, will we get out of there alive, right? And that's very much a long-term question and not just a question, you're going to be fine for a second, as far as I can tell. And that's where the dynamical systems challenge comes from. Now, believe it from someone who just recently broke his foot in too much soccer, it turns out that motion is a present. But the presence of motion also requires us to look at the future of motion in order to predict where are we going to go end up. Is that free of collision? And that's something that's not just true in soccer, that's also true in the flight of aircraft, or the motion of cars, or as trains run through the corridor environment. And in fact, that's where it turns out that Niels Bohr, of course, already said everything in much better ways than I could, because he said prediction is very difficult, especially if it's about the future. Sadly, it's only the predictions about the future that really help us. All right, I'm not going to talk about any of the many applications of the differential logic that Studio Olderock already gave away, that I had my hands in developing those. Has been good for, nor how my students found 15 billion mistakes in the next generation airborne collision avoidance system developed for the FAA, because I believe it is infinitely more important to emphasize what you do to then ultimately fix the problems and make sure that they're gone. In fact, I would also argue that you should all be talking to my students, if you won't mind standing up for a moment. These are the people you want to talk to if you want to find out more about those applications, because honestly, they can tell you better than I ever could. But of course, I'm a logician, which by heart, so that means when I talk about solutions and correct predictions about dynamical systems, I will do this in logic. and I would feel I would take an extremely exciting opportunity away from you to appreciate the value and beauty of logic if I wouldn't actually show you lots of logical formulas. So Maike already showed you how to do that, and I'll just follow in her footsteps. Differentiating logic, that's my baby, and I believe it's important. It's not anywhere near as clever and as important as my son is, Leon, who was in the audience with me, but differentiating logic is also kind of important and kind of useful, because you can use it to describe the behavior of your favorite application, and then ask prediction questions about it, and even better yet, ultimately actually answer those prediction questions. And I'll show this to you with my favorite example, which is the Wall-E robot. This is my favorite dynamical system, and this logical formula here is going to turn into one logician, I promise. This logical formula here says all behavior of the Wall-E robot is such that Wall-E's position is different than the obstacle's position. And what that means is, no matter where Wall-E goes to, Wall-E's position x, which will be different in different future states, will still nevertheless always be different than the obstacle's position. And that would be a good property to have, because that means, hey, if Wall-E never collides, we can turn Wall-E on. Unfortunately, for Wall-E, we need to become more precise what Wall-E looks like. Here's a dynamical systems program, it's called a hybrid program, with which we describe what Wall-E does. I'll read it to you. Here it says that if a certain step breaking point is true as a function of Wall-E's position and the obstacle's position, then I guess we change the acceleration variable to a negative value, minus b. And when we're done with this discrete dynamical control algorithm, then we're following an entirely different mode of the system, a differential equation, which is a continuous dynamics. We follow the differential equation x prime equals v and v prime equals a. Wait, what does that mean? That means that we follow the time derivative of the position equaling the velocity, while the time derivative of the velocity equals the acceleration. And in fact, that's mostly harmless. This is kind of the easiest possible differential equation you can write down, but it has the benefit that it fits on the slide. So that's the one I'll talk about. Now, here I have now the logical formula that says always when I do that, and when I repeatedly do this is Kleinius star operator hidden here carefully for your pleasure to make sure that we understand that we iterate discrete and continuous operations to get this trajectories like this. Then the question overall is Wall-E's position different than the obstacle's position? And if it would be safe to turn Wall-E on. Sadly, this is not a true formula, but it is only true under certain assumptions, yet logic is brilliant at managing assumptions with an implication. So if this is true, then the Wall-E robot is safe. And the assumptions at least have to include things like it's good not to start in a collision state, because we won't always be collision free if we start crashed up. It would be very helpful if the brakes work and other things like that. But at some moment in time, you'll have sufficiently many assumptions so that this is actually a true statement, at which moment you would even better like to have a justification for why this is a true statement so that you can tell your friends about it. Or maybe send it off to TÜV for the justification why the Wall-E is a safe robot to be using. Now, let's get more systematic, right? I'm a logician, I have to be systematic. So here we are. This is differentiating logic, and you can have assignments for primitive discrete change computation. Computer scientists are good at changing things. So this is how we do it with an assignment that puts a new value in a variable x. More importantly, to some extent, however, is the differential equation. X prime equals f of x. That we follow for a certain period of time, as you appealed to it in his wonderful speech before, within a certain evolution domain Q. So Q is describing how long we can do that sort of thing, right? Things like after 10 hours, maybe stop and do something else because it got boring. Or maybe when you're going too fast, maybe decide a bit differently. That sort of thing goes there. And then here's the programming language researcher in me, the other operators, for instance, that of a choice. There's a choice between alpha or a beta. And for instance, when I'm flying my son's model airplane, there's literally no control over whether it's flying up or down. It's just anything happens. When my son is flying it, there's a lot more cleverness in the flight, but even then, there's still the branching behavior. Sometimes he's flying up and sometimes he's flying down. The sequential composition is that of one step at a time computation. So first, we're doing alpha and then we're doing beta. For instance, first my son will fly the aircraft up to a safe altitude, at which point he will hand over control to me so I can fly with beta and not even me will be able to damage the plane anymore. Repetition is also very important. That's the Kleene star. That says we now do this over and over and over again. So for instance, it will take lots and lots of control cycles to correctly and safely fly the model airplane all the way to the Paris airport. But that was all just for describing the dynamics, and you can describe every hybrid systems dynamics in these programming languages. But we also want to ask questions about them in order to be able to form predictions about them, and that's where differential logic formulas come in. They start out like logic always does, for instance, with an implication, P implies Q, and quantifiers of the reals, never mind. But what's important is that for any dynamical system written down as a program, alpha, and for any differential logic formula, P, written down like so, is alpha box P and alpha diamond P, yet one more formula, and they mean that all behavior of the alpha dynamical system is such that the only states you can reach are the ones that are safe according to the condition P. And beta diamond is sort of the dual. It says that if you just wait long enough, ultimately your airplane will have landed in Paris. And these two pairs of logical operators are brilliant for stating, for instance, safety, it's always good, or aliveness, eventually I'll be there, properties. But now it's a full logic closed under all the operators, so you can start nesting things. And for instance, say there is a beta run such that all alpha behavior makes us happy. And that's the level of nesting that you need to, for instance, express stability properties for these systems. And that kind of gives you an indication why differential logic is sort of the logical lingua franca of control. You can ask any question you like. In a formally precise, rigorous way. Now, only being able to ask questions is not as useful as also being able to answer some of them. That's where we're going next. But I could have given you lots of these picture intuitions in pure, beautiful math on this slide as well. I'm not going to do it. I just want to mention that this is easily possible by a simple inductive definition. Okay, maybe now that you're all looking, I'll point out one point about it. For instance, you can say the meaning of a program that has a choice is just the simple function, a union of the left-hand side and the right-hand side, and it makes some sense. You know, a program that has a choice between two behaviors, either does one or the other, and nothing else. Right? And the point I want to make with this is that this is a compositional semantic. So the meaning of a slightly more complicated program is a simple function of the meaning of the pieces. And that compositionality in the very design and structure of the logic is exactly what we will be exploiting also for the analysis, because it will enable us, if we do this right, to also prove in a compositional fashion, prove the whole system as a function of lots of little proofs about little pieces. Let's go exactly there. Proofs for dynamical systems. Here we are. It's these axioms of differential logic that are equations of truth, essentially. They equate this logical formula with that little formula, and they say the two have the same truth value, which means no matter where you are in the understanding of a system, you can simply replace things for their equivalents. It's like equality transformation. You can do this all day long. You're never going to change the truth value of it. However, the point is, by using it from the left to the right, you're also making it easier. Careful people might notice that it got longer. On the other hand, logicians will tell you, well, be that all as it may, the program is a big one, it's a choice, and here's lots of small programs, and I can only make things smaller finitely often, and then it will become trivial. Okay, let's illustrate it a little bit more. So here's this principle that a system that has a choice between alpha or beta will make us happy if and only if all the alpha behavior makes us happy and independently all the beta behavior makes us happy. And that really is self-evident. And that's kind of the point. All of those are very simple reasoning principles that you buy into once and then you can just syntactically use forever. It's like the addition theorems of differential calculus. You understand them once and you just use them from now on. Down there is maybe my personal favorite. It says that a system that repeats is safe if and only if we start safe, and no matter how far we already repeated, if we are still safe, then we're safe in one more round. This is an induction principle cast into the principles of logic. Very beautiful. All right. Now, since Ernst Rüdiger Oldrock mentioned it earlier this morning, I can't help but, earlier today, I can't help but mention that, oops, what's going on here? I can't help but also admit to the fact that for the logic connoisseur in the audience, I would like to share briefly the soundness and completeness principles of differential logic, which not only means that every formula you prove in the logic is actually a true one. So it's called soundness. Every sound that a logician makes is sound. So in the sense that it's correct when they say that. But also the other way around. If it's true, there's a proof for it from very simple, in comparison, elementary properties of either differential equations or discrete dynamics. All right. Let me let that sink in for a moment and easily fast forward to the question, I guess it's then interesting to prove properties of differential equations, because exactly as good as I could do that, could I prove properties of arbitrarily fancy, crazy, weird dynamical systems? And that's what we're doing next. There's two examples here. One of them says, if we start inside the green region, we will always stay inside the green region when we follow this differential equation, which I've plotted here for you, because that's easier to look at. Now, it is true, if you follow these vectors from anywhere inside the green region, you will always stay inside the green region. But you would like to have a proof if your life depends on it, which it won't for this example, but which it would if I had used the differential equations with an aircraft. And indeed, the classical mathematical reflex when looking at a differential equation is someone emails you a differential equation, the first thing you do with it is solve it, and then look at the solution. Sadly, that's the wrong way of working with them, because that undoes the entire descriptive power of a differential equation. They were really only invented in order to describe fancy, crazy, weird processes in simple ways, because they only look at the behavior completely locally. And I'm not the first one to say that. That is what Henri Poincaré already said in 1981. What is going on here? In 1981, when he called for the qualitative theory of differential equations, and in differential logic, can you look at the global properties of differential equations and prove them solely from looking at the logic of the local change? That makes them so interesting. Let's look at how. At the top, you see that all behavior, again, me with my logical formulas and so on and implications, but all behavior of a differential equation is such that an inequality is true afterwards, so E is greater or equal 0, if E starts greater or equal 0, and all the time the differential or derivative or something like that of E is greater or equal 0. It makes some sense. If you start above 0, your rate of change is above 0, I guess you stay above 0. Yeah, makes sense. This is the principle of differentiation cast in logic. I believe there should be at least one new result per talk. Here's the new result. This one says that for equalities, it's a bit different. You have an if and only if arrow. So in the future, inequality is true if and only if some stuff is true right now. And that's a property that logic and ancient lore and medieval times have in common. It's very important to pay attention to which direction the arrows go. Here it's an if and only if, so it's true, the left-hand side is true exactly when the right-hand side is true. When it's for inequalities, it's only one direction. All right, this is reasoning by differentiation. You can also reason by accumulation of knowledge, where you show that if I know that my system never leaves the region C, so in pictures it never goes out of C, I might as well assume C from now on. I guess that makes some sense as well. If I know I can't leave C, it doesn't hurt if I assume it. And that's, however, formally an editing of the system assumptions. An editing of assumptions seems a priori like a very dangerous operation to do, but after you have a proof that it was okay, I guess this will pass. Differential ghosts is the most spooky of them all, but also my personal favorite. It now edits the differential equation itself. It changes the differential equation to a new differential equation, y prime equals a of xy plus b of x, that was never there before, and we dream it up just in a way to make our analysis easier. Okay, why should that help? Well, this is reasoning by differentiation. This is reasoning by accumulation of knowledge. This is reasoning by editing or adding differential equations, which is ultimately reasoning by integration. And it turns out all three of them is the only thing you need in order to prove every true invariant of a differential equation in a sound and complete way. It's pure logical rewriting leading you to a decision about the predictions of the future, and it doesn't get any better than that. So, in fact, what you can logically, just simply syntactically derive in a computer is that an equation is true always in the future when following a differential equation, if and only if, here I come with my arrows again, a differentially transformed equation is true right now. And that's precisely an equivalence between future truth and present truth. And that's the heart and soul and core of every prediction. You're trying to relate a property of the future to a property you can see right now. And here you have an equivalence between the two, which means you will exactly be able to tell which equations are true in the future and which are not true in the future. Now, for inequalities and stuff like that, it gets a bit more complicated. It's written down there, but you get the basic idea. All right. I promise not to talk about any applications, so I'm not going to do that. Instead, I would much rather show you the principle that we're following, which enables you to do your own favorite application. And Ralf, I want you to appreciate in person that this is as close as a logician will ever get to a process, right? This is a genuine picture of what you do, so listen up. You start with your favorite system, the one that matters to you, right? You write down a model for it. That seems like a good thing to do, because if you want to predict the behavior, you can't just say, yesterday my car didn't crash, so I guess it'll never. You have to say, no. What's the general behavior that cars can have? In order to be able to then, by mathematical logical proof, be able to predict everything that they could ever do. If that's then safe, that's the moment when I would personally feel comfortable to turn the key and start the engine. In particular, maybe go to sleep and let the car control handle it. Maybe don't do that. I need you guys. So, but the point is still, this is like how you should be operating along those lines. Then in our Chimera X theorem prover, which we already heard, is actually secretly based in all its ideas on the key prover, which comes from KIT, for instance, and from Darmstadt and from Chalmers and so on, places like this. With this, you write down a proof of the safety of the model of your system. Now you pat yourself on the back because you have a proof of correctness of the control according to your safety questions in the model of the system. But you could have written down the wrong model of the system to begin with, right? You wrote down the model of the system and not the system. Okay, this is a fundamental challenge, but can be overcome as well with even more proof that you still do in Chimera to synthesize by proof a provably correct monitor of reality, which will then bridge any gap that could still exist between the model and the reality land. And then you're good. Let me summarize. So, in logic, you've seen the logic of dynamical systems, which is differential logic. Admittedly, it's the base case. I have a whole pack of logics that can do more and more and more of those things. But the point is, differential logic is your logic of choice whenever you're looking at systems that have both discrete dynamics, so one step at a time computation, which is what computers and controls are good, and continuous dynamics, which is the thing that aircraft tend to be good at if you turn them on. They continuously fly through the air, or a robot that's continually wiggling on the floor. Hi, Tamim. But there's also extensions, for instance, for adversarial dynamics, whenever you have multiple agents that don't get along with one another, or whenever you have multiple agents that are possibly interfering in their actions and so on. And it turns out they're actually playing a hybrid game and no longer necessarily just following the dynamics of a dynamical system. Or you could have stochastic dynamics or autonomous dynamics, etc., blah, blah, blah. The point is, in each of those cases, does logic give you an exceedingly strong analytic foundation to build on so that you can rest assured that everything you ever say is okay. You also have lots of roll-up-your-sleeves practical reasoning advances in the theorem-proving land, and that enables you to do exciting, significant applications and bring lots of areas of science and engineering together. The key secrets in what I've told you so far is that logic and proofs are exploited for dynamical systems principles, that there's a lot of compositionality principles from me being a programming languages researcher. There's a lot of secret tricks and cleverness in the theorem-proving land, and exactly the important principle that systems are actually multi-dynamical systems. They're characterized by multiple facets of dynamical systems: discrete, continuous, adversarial, autonomous, stochastic, distributed, what have you not. In fact, I also want to admit to a sad fact about logic that sometimes logicians just don't know. Yet, but the good news is if they say something, they actually know it because of the soundness, right? So there can be no confusion about that. I think also logic matters because there's nothing just like logic to discover eternal truth because, well, I have a proof. What could possibly go wrong now that I have a proof? Oh, reality, okay. Henri Poincaré, of course, already said this in a better way. He said that it is by logic that we prove, but it is by intuition that we discover. So we need the logicians to be able to do all those proofs, but you need your intuition about the systems in order to guide the proofs and make sure you're running in the right direction. In fact, this is, I think, also another thing I wanted to share with the young generation of junior scientists, students, and so on. I personally at least believe that we need a few things for success in science. It's, I believe, a mix of inspiration and foundation because we need the inspiration to make sure we're running in the right direction, and we need the foundation to make sure that we arrive in one piece and hasn't all fallen apart. But we also need passion because we're only at our best if we're following the things that really matter to us personally. And at least in my case, I found that. It's all this game with logic and dynamical systems. And in fact, just 2 weeks ago, a good friend, Dominique Méry, told me that he found me out, except that I have made a mistake, by calling it DL, little dl, differential dynamic logic, because I should have called it DDL, because obviously Dédé in French would have been the diminutive version for André, so the appropriate way of referring to me if I would be this tall and running around and giggling. Now, don't get your hopes up. I may still run around and giggle, but I'm a little bit taller now. But in fact, the actual thanks goes back to my parents because they had the clever foresight of installing a differential operator right in my name. So it's clear that I'm doing the kind of research I need to be doing. So thank you so much.